Dear colleagues, we offer you a report on the topic multilayer thin film resistive structures with temperature self-compensation for super precision resistors and strain gauges. The development of information and measurement systems for the management and control of a new generation of equipment is characterized by an aggravation of the problem of accuracy and reliability, as well as the emergence of new technical requirements for stability, miniaturization, speed, etc. For these reasons, there is an interest in systems and sensors built using thin film microelectronics technology that can function with specified requirements in constantly evolving operating modes. For this reason, the purpose of the article is to consider constructive and technological solutions for creating multilayer thin film precision resistors with the possibility of temperature-resistant self-compensation. Thin film resistors, chip resistors and sensors built using thin film microelectronics technology are complex physical devices representing a set of interacting elements integrated into a single system. The small dimensions of the basic structures, which reach submicron sizes in some elements, determine the significant influence of external physical influences on their functional properties. Comparative characteristics of the available level of the best foreign and domestic precision resistors are shown in the table on this slide. It is possible to achieve a qualitative improvement in the characteristics of samples only with the study and knowledge of the relevant properties of materials, as well as the introduction of new functional layers into ready-made structures, the parameters of which allow achieving advantages over the industrial analogs used. Experimental studies of existing resistive materials for the manufacture of heaters and analysis of the literature showed that the best results in terms of time and temperature stability are given by metal silicide resistive materials and materials based on nichrome. According to theoretical studies, the electrical conductivity of metal silicide pairs is due to the presence of two components, metal and semiconductor, thermal activation. An analysis of the above ratio gives reason to believe that it is possible to obtain a TCAC close to zero. However, taking into account the uncontrollability of the vacuum deposition process and the multivariance of the resistive film formation modes, it is not possible to formulate technological criteria for the controlled synthesis of thin films, the TCAC of which would be close to zero in the operating temperature range. In practice, according to the selected deposition modes, the TCAC values of ceramic film resistors with a probability of at least 95% lie in the specified range. The definite alloy has proven itself in the best way as resistive films based on nichrome. In the case of correctly selected spraying modes, TFF based on nichrome have a positive TCAC sign lying in the range from 5 to 51/ without preliminary annealing and temperature adjustment. According to the source, the distribution of elements over the thickness of the TFF due to the fractionation of the alloy is presented. The analysis was carried out by the method of secondary ion time-of-flight Massachusetts spectrometry. Pure Ki lies on the surface of the dielectric layer, the ratio of Ni to our ferrolina changes closer to the center of the tar film, and nickel coated with oxide lies on the surface. Over time, the final formation of phases and recrystallization, on the one hand, and surface and bulk oxidation of chromium, on the other, are possible. The speed of the first process depends on the optimal modes of thermal stabilization and is minimal with the proven technology, and the second on the chromium content in the resistive layer. In this case, the temporary drift of the T-reter resistance based on K-20s and K-30s has a negative direction. By choosing in a certain way the ratio of the thicknesses of layers with positive and negative TCAC in a two-layer thin film structure, it is possible to realize self-compensation of the temperature dependence of the resistance of such a thin film solid solution. The resistance ratio in this case is calculated according to the formula shown on the slide. It should also be noted that the temporary drift of resistance for these pairs has opposite directions, which can also theoretically reduce instability. For highly stable heaters with temperature self-compensation due to the proposed two-layer structure, two main problems are solved in the process of developing the technology. At the first stage of the technology development, a variant of the multilayer TFF material was determined, which will be the lower layer of the formed structure. At the second stage, the technological modes of stabilization and adjustment of the TFF were determined by high temperature impacts and vacuum and air. Material with a positive TCAC sign was sprayed first. Therefore, the lower TFF layer was nichrome. The weak-linked chromium film is its sensitivity to moisture. As a result of exposure, resistive paths are set and etched due to electrochemical corrosion. To avoid the defects shown, nichrome films are covered with protective films. For freshly precipitated TE-tears based on any materials, a heterogeneous and stable structure, non-equilibrium concentration of defects and other imperfections are characteristic, which leads to a change in resistance, both over time and under the influence of high temperature due to an increase in structural homogeneity, removal of residual stresses. Therefore, immediately after spraying, thermal stabilization of the resistive layer is carried out in vacuum. The modes of thermal stabilization of the formed TFF from alloy are performed in two stages: thermal cycling in vacuum, heat treatment in air. In order to develop the necessary stabilization modes and achieve the specified temperature time stability, additional temperature tests of the TFF from alloy were carried out in air at a temperature of 250 C. The results of the T-retear resistance measurements during the tests are listed in the table on the slide. According to the results of temperature tests in air, it can be seen that the change in the resistance of TFF from alloy is insignificant. Therefore, it was decided to stabilize the obtained multilayer TFF by a combined technology in a vacuum and the presented form. After all the operations to stabilize the parameters, the TCAC was calculated. According to the obtained results of the work carried out, the possibility of self-compensation of the temperature dependence of the resistance of a two-layer thin film TFF with resistive layers of alloy and K-20s was established. A technology for obtaining a multilayer resistive structure has been developed, and modes of stabilization of the parameters of finished TE-tears have been determined. Thank you for your attention.